The paper is Parietal alpha frequency shapes own body perception by modulating the temporal integration of bodily signals, and it was published in Nature Communications on January 12, 2026. Let's do the quick summary. Researchers at the Karolinska Institute they've effectively identified the clock speed of human consciousness. They found that the frequency of alpha waves, that's between 8 and 13 hertz in the parietal cortex, acts as the brain's sampling rate for reality. This frequency sets what's called the temporal binding window. That's the tiny slice of time the brain uses to decide if two different inputs, say seeing a touch and feeling a touch, belong to the same event. And crucially, they proved this wasn't just a correlation. Using magnetic stimulation, or TACS, they could actually speed up or slow down these brain waves. And by doing that, they could change where a person perceived the boundary between their own body and, the outside world. It proves the brain solves this huge multisensory problem using specific oscillation frequencies. It's basically defining the computational limits of you.
That is a massive claim. And, usually on AI Paper Podcasts, we are all about the latest transformer architecture, maybe some new sparse autoencoder.
Right, or a diffusion model.
Exactly.
Yeah.
But this paper, it just blew up on Hacker News. It stayed on the front page. And I think I know why. It's because we're finally seeing a biology paper that treats the brain like a piece of hardware, a signal processing unit.
Yes. That's it. I mean, you read biology papers and it's all ion channels, neurotransmitters. This one talks about sampling rates, latency windows, integration thresholds.
It's our language.
It's our language. Yeah. And seeing it applied to the wetware in our skulls it's just fascinating. It's like we're finally reverse engineering the ultimate black box.
We really are. And to get why this matters so much to an engineering audience, you have to look at the problem the brain is even trying to solve here. It's called the binding problem.
Which is pretty much a distributed systems problem, isn't it?
It is. Absolutely. Your brain has all these different input channels. You've got vision, touch, hearing. They're all nodes sending data back to a central processor. But, and here's the catch, they all have different latencies.
Right. The physical wiring is different.
Totally. Light hits your retina and gets processed way, way faster than a touch signal that has to travel all the way of your spinal cord from your foot.
So you've got these asynchronous data streams all hitting the server. The packets are out of sync.
Precisely. And the brain has to make a simple binary choice. Do these two signals happen at the same time, and do they belong to me? If it messes up that logic, your whole sense of reality just falls apart.
And they tested this with the classic rubber hand illusion. I've always loved that one. It feels like a unit test for consciousness.
It is a unit test. For anyone who hasn't seen it, the setup is actually deceptively simple. You have a participant sit down, and you hide their real hand behind a screen. Then you put a realistic-looking rubber hand in front of them where they can see it.
So I'm looking at a fake hand, but I can't see my real one.
Correct. Then you get these little robot arms to tap both the real hidden finger and the visible rubber finger at the same time. If those taps are perfectly synchronized, zero latency, something amazing happens. The brain just performs a merge operation.
It overwrites the self pointer.
That's a great way to put it. It basically says, okay, that rubber hand is mine. You literally feel the touch on the rubber hand.
It's like a buffer overflow exploit for the senses.
It is. But here's where the signal processing comes in. The key variable is the lag. They didn't just tap them at the same time, they started introducing delays.
So they messed with the timing?
They varied the asynchrony.
Right.
Maybe the visual tap happens 100 milliseconds before the felt tap, or 500 milliseconds after. They wanted to find the breaking point. How much lag can your system tolerate before it throws an error and says, nope, not me?
And this is where we get to the core of the paper, the alpha waves.
Right.
We hear about alpha waves all the time from meditation apps, get into an alpha state. But that's not what this is about, is it?
No, not at all. In this context, think of alpha waves, which oscillate around 10 times a second, 10 hertz, as the clock speed of your parietal cortex.
Yeah.
That's the hardware in your brain that maps your body and your senses.
Okay.
And the hypothesis is the brain doesn't process reality in a continuous stream. It samples it. It takes discrete snapshots.
So we're not analog, we're digital.
We're discrete samplers. That's the theory. And each of these alpha cycles is like a single perceptual frame. If a visual signal and a touch signal both land inside the same frame, the brain binds them. It says these happened at the same time.
But if one lands in one frame and the other lands in the next?
It segregates them. It says asynchronous.
That's literally the refresh rate of a monitor or the sampling rate of an analog to digital converter.
It is the exact same concept. And this is what they found in the first couple of experiments. They measured every participant's individual alpha frequency, their IAF. And just like CPUs, there's, variance in the silicon. Some people run at a slower frame rate, maybe 8 or 9 hertz. Others are basically overclocked at 12 or 13.
And that predicted their perception of reality.
Perfectly. The people with the slower alpha frequency down around 8 hertz, they have a longer sampling period, about 110, maybe 120 milliseconds. So their temporal binding window is really wide.
They're low-resolution samplers, so they're easier to fool.
Way easier. Because their frame is so long, you can have a pretty big delay between the vision and the touch, but if they both fall into that one big bucket, the brain just goes, yep, synchronous. So they accepted the rubber hand as their own, even when the tapping was really laggy.
Whereas the people with the fast alpha waves,
The high refresh rate people, the ones at 13 hertz, their sampling period is much shorter, maybe 90 milliseconds or less. Their binding window is narrow.
so they have high temporal resolution. They notice the lag.
They notice it immediately. The visual tap lands in frame 1, the felt tap lands in frame 2. The brain just says error, asynchronous, and poof, the illusion breaks. They reject the hand.
Wow. I mean, that's incredible. It implies that your whole grip on reality is just a function of your hardware's clock speed. But correlation isn't causation. We know that.
Right.
Just because I have fast alpha waves and I'm good at spotting lag doesn't mean the waves are causing it.
And that is exactly why this paper got into Nature Communications.
Mhm.
They didn't stop at correlation. They went for the causal proof. They did experiment 3.
This is the overclocking experiment.
But essentially, yeah. They used TCS transcranial alternating current stimulation. They put electrodes on the scalp right over the parietal cortex and zapped it with a tiny electrical current to entrain the brain waves. They literally forced the brain to oscillate at a specific frequency.
Can we just pause on how cyberpunk that is?
Yeah.
They are externally setting the clock speed of a human brain with a battery.
It is wild. So they had 3 conditions. Condition A, they stimulated the brain at 8 hertz, forcing that slow, low-res state.
Okay.
Condition B, they pushed it up to 13 hertz, forcing the fast, high-res state. And then a sham condition as a control.
And it worked. It changed their behavior.
Drastically. This is the smoking gun. When they slowed participants down to 8 hertz, their temporal binding windows widened. People who were sharp before suddenly couldn't tell. They got worse at detecting the asynchrony.
So they felt the illusion more strongly.
Much more strongly. The boundary of their self literally got blurrier because their sampling rate dropped.
Yeah, when they sped them up to 13 hertz.
The complete opposite. The window narrowed. Participants became hypersensitive to lag. Their definition of self got stricter, tighter. They rejected the illusion because their brain was refreshing fast enough to spot the error.
So alpha frequency isn't just a byproduct. It is the mechanism. It's the control dial.
It's the dial. And for all the machine learning folks listening, this is where it gets really, really cool. Because they didn't just stop there. They modeled this whole thing using Bayesian causal inference.
Yes, I saw that. They built a computational model to explain why this happens, because the brain is basically a prediction engine, right? Is predictive coding.
Exactly. The brain is a probabilistic inference machine. It's constantly weighing 2 things: the sensory evidence coming in and its priors. A prior is just a built-in assumption, like my hand belongs to me, or vision and touch usually happen together.
It's a standard Bayesian update then. You have a prior belief, you get new data, you update your belief.
Precisely. Now, the big question was, where does alpha frequency fit into that equation? And what they found was that it maps almost mathematically to the parameter of sensory uncertainty.
Okay, let's unpack that. How does frequency equal uncertainty?
Well, think about sampling again. If you're sampling at a low frequency, say 8 hertz, your data is sparse. You have these long gaps between each sample. In signal processing, that's high uncertainty. You're not sure about the precise timing of an event.
Your data is temporally noisy.
Exactly. So if your sensory data is uncertain or noisy, what does a Bayesian system do?
It falls back on the prior. It trusts its assumptions more.
Bingo. That's the key. If the incoming data is fuzzy because your sampling rate is low, the brain says, look, I'm not sure about this timing, so I'm just going to default to my prior belief that this hand is mine, and the illusion takes hold.
The prior belief overrides the clumsy data.
It does. But then if you use TECS to ramp that frequency up to 13 hertz,
Your sensory uncertainty drops. The data becomes precise.
and when the evidence is strong and precise, it overrides the prior. The brain looks at that high-res data and says, nope, the timing is clearly off. I trust this data. That is not my hand.
That connects so perfectly to predictive coding. It suggests the precision of our bottom-up sensory signals is literally hardware constrained by these oscillation rates.
It gives a physiological anchor, the alpha wave, to a computational parameter, uncertainty. It's not just an abstract model anymore. We can point to the electricity in the parietal lobe and say, that's the uncertainty variable, right there.
So, okay, we have the mechanism, we have the causal proof, we have the math. What does this actually mean for us? What are the applications? Because if we can hack the frequency, we can hack perception itself.
The paper points to two big areas, clinical and technical. On the clinical side, they talk about schizophrenia.
Right, which is often defined by a disturbed sense of self.
Exactly. And there's already research showing that patients with schizophrenia often have slower alpha rhythms. So if you apply this paper's logic, it suggests their brains might be running with a really wide temporal binding window.
They're over-integrating reality.
Yes, they might be binding unrelated signals too aggressively. If your window is too wide, maybe you attribute an external voice to your own thoughts or an external event to your own actions. The boundary is just too porous.
That's fascinating. So you could potentially use TACS to speed that rhythm up to help tighten their reality testing.
That seems to be the implication. And then you have amputees and phantom limbs.
How does it apply there?
It's a similar problem of ownership mapping. If you can manipulate this binding window, you might be able to help a brain accept a prosthetic limb more easily. If you widen the window a bit, the brain might be more forgiving of the slight mechanical latency in a robotic hand.
Which brings us right to the tech angle. VR and robotics. We talk about latency in VR all the time.
This changes everything for VR developers. Right now, we optimize for an average human. But this paper says there is no average. There's a whole spectrum of alpha frequencies.
So a user with a high alpha frequency, one of these high-res people, is going to get simulator sickness way faster than a low-res person.
Of course. The high alpha user will instantly detect the lag between their physical hand moving and the virtual hand moving. The low alpha user might not even notice.
So in the future, a VR rig should run a calibration test when you first put it on.
It absolutely should. It should measure your individual alpha frequency. Then it knows your exact temporal binding window. It knows how much slop it can get away with in the rendering pipeline before your brain throws an error.
Or, and here's where it gets a little wild, could the headset induce the state that it needs?
That's the real hacker angle. If you have a BCI integrated into a headset, could it use non-invasive TCS to temporarily slow your alpha rhythm down to 8 Hz while you're in the game?
A game mode for your brain.
Literally. Cinema mode lowers your brain's refresh rate. You could effectively mask the system latency. You widen the user's window of acceptance and make a 50-millisecond lag feel completely instantaneous.
That is both incredibly cool and also a little terrifying.
It's optimizing the user to fit the hardware, not the other way around.
And prosthetics.
Same exact principle. If you want a robotic arm to feel like it's part of you and not just a tool you're holding, the sensory feedback has to arrive inside your specific alpha cycle. If we can tune the feedback loop to the user's alpha, or tune the user's alpha to the feedback loop, we can cross that uncanny valley. The tool becomes the body.
This just brings up such a huge philosophical point. We all think of ourselves as this continuous, unbroken stream. This paper says that's a total illusion. We're a flip book, not a movie.
We are absolutely a flip book. We just turn the pages fast enough, about 10 times a second, that it feels continuous. But the you in frame 1 is structurally distinct from the you in frame 2. And the machine that stitches it all together can be hacked with a 9-volt battery.
That is the takeaway right there. We are signal processing units and our variables are exposed.
Yeah, it reframes what human augmentation even means. We think of adding a chip, adding hardware. This suggests we can augment ourselves just by tuning the hyperparameters of the software that's already running.
Tuning the hyperparameters of consciousness. I love that.
It does raise a final question for me, though. If we can artificially tighten or loosen the boundary of the self, how far could we push it?
What do you mean?
Well, we saw that slowing the waves made people accept a rubber hand. What if we slowed them down even more? And what if we optimized the feedback loops from, say, a car or a piece of software?
You think you could make a car feel biologically part of you?
If you could perfectly synchronize the vibration of the engine and the visual flow of the road so they fall inside a massively widened alpha window, could you induce body ownership of a Honda Civic or a code editor? Could you make compiler errors feel like actual physical pain?
I think some developers already do.
Fair point. But technically, if we can mask latency by slowing the brain's sampling rate, we might be able to integrate external tools so completely that the brain just stops seeing a difference between the hand and the hammer.
That is a provocative thought to leave you all with. The limits of you are not defined by your skin, they're defined by your refresh rate, and that rate is adjustable.
It's just a parameter.
Thanks for joining us for this look at parietal alpha frequencies. It has been a mind-bending one.
My pleasure.
Check out the full paper in Nature Communications if you want to see the math for yourself. We'll catch you on the next one.